By the way, tonight needs to be done on graph paper too.
Oh, okay. Well then. Well, we're doing parallel. No, we just did parallel lines.
I miss construction. Back then things were so much easier.
Oh yeah.
All right. If you didn't hear what I just said, what is it? Oh, if you didn't hear what I just said, you're going to need graph. You have to have graph paper to do tonight's homework. So it is done on graph paper. I forget how many questions there are. You will not need it for class now, but you will need it for homework.
Sir, how many chapters are in this book?
We are on the second to the last chapter, 14.
How many chapters do you truly care about in this book? Thank you for your validated answer.
There, 14 covers transformations. So transformations are one of those things, with the exception of dilation, which is the only one that we haven't mathematically done. If it was just on dilations, I'd said it was important, but reflections, rotations, dilations are with the exception of dilations, are all stuff that we've covered in other classes. And there's nothing really to prove for those. Questions on homework?
No.
Oh, I promised you an answer.
Oh, yeah, safety.
And it was ridiculously simple, and simple things never strike me as simple. I need quiet to think it through. So we were given this one, we were given this one, and we were given this one. We were not given this one. Well, it turns out that we prove in A through whatever that it's a rectangle, right? So if it's a rectangle, we know that these two slopes are exactly the same.
So you just take the you just take that.
Yeah. If they're exactly the same, then we just calculate their slope, right? Whatever this run is and whatever this rise is, you apply it to this, to that. In other words, I'm making numbers up. I want to say the slope was 5.5, if I remember right. I think it's 5.5. Is that right? This is number 6D or something like that. Is that right?
Maybe.
Yeah, it's 6.
Yeah.
And I believe it's 5.5 is the slope. Like if you look at the coordinates of the x's, you look at the coordinates of the y, they're 5 off from each other. So then all you do is you're given this coordinate, I don't know what it is, negative something. You just apply 5 up and 5 right to those numbers right there, and you get the answer.
Which is?
Well, give me the numbers.
I
do remember, because I did in the other class, it was 5.5 was the slope, but I don't remember what this coordinate was right here.
Oh,
what was this coordinate right here?
That one right here was a
what is it?
-2, 6.
Positive 6?
No, -6.
All right, so we need to go up 5. So if we go up 5, we're going to be at
3. -1.
And if we go
3.
right 5, we're going to be
7.
3. So
Number
3
that is
-1.
not divisible between 8 and 2.
And that is the right answer. 3 -1 for 6D. And that was we did A, B, and C in class.
There's a lot of stuff to go over in this one.
Well, for instance, number
7 and 8 have 6 answers each.
6.
Yeah, because you had to figure out the
3
slope,
answers.
and then you had to figure out the altitude of the slope.
Oh yes, that was complicated, wasn't it?
No, it wasn't.
Well, I mean, it was complicated in the sense of you had to do 6 things for each question.
Yes, it's complicated going on to
Right, but it wasn't that big of a deal to do it though. By the way, remember, we didn't do one like in class. I probably should have thrown one of those for practice, but an altitude is a line that's perpendicular to a side. So once you find the side, then you have to figure out the slope of this to figure out what will be perpendicular to it.
Hey, I do have a question for one.
Yeah.
16. Decide what special type of quadrilateral HIJK is. The 4 coordinates are H is 0, 1, I is 2, -3, J is -2, -1, and K.
I haven't done this in a while, but just so you guys have at least seen me do this once. I can't do that. Hold on 1 second. I got to change this first. Okay. Share. All right, you guys have seen me in the past use Desmos once or twice?
Yes.
All right, give me the coordinates.
All right, number 1 is 0, 1. Number 2, 2, -3. -2, -1, and -4, 3.
So by observation, let me make this a bit. And if we play connect the dots, what's it look like?
Looks like a
It looks like a parallelogram. So what does it say? We have to prove it. Now, could it be a rhombus?
Yeah.
Could be.
We would have to figure out the distance. So we have to use a distance
But they're not
formula.
all the- But I've already done that. They're not all
They're not all the same.
the same.
Okay.
Parallelogram.
Is the slope the same? So it's down 2, right? 1, 2, 3, 4. So that's -1/2. Yeah. So the slopes are the same. Absolutely. Just the question of, is it the distance the same? We'd have to do that, man. You're saying you did the math and they're not the same?
I said that I do not think they are.
Well, we got to pick a couple of them and figure it out.
Or you can just look in the book and answer.
Well, I know that, but where's the fun in that? All right. So what do you want to go? What color to what color?
Let's go yellow.
Which ones do not look like?
Let's go yellow to red.
There's a yellow one.
All right,
Are you
fine.
colorblind too?
I'm colorblind.
Okay, fine. Blue to orange.
All right.
No, green to orange.
It's not.
That's not part of the side.
Oh, okay, purple to blue.
Purple to green.
Now we could, if it's a rhombus, we're going to find out they're perpendicular.
Exactly. So that's why purple to green.
Okay, purple and green would be right. And then we got to do one more.
Orange to blue.
That's red.
Okay.
That isn't-
I mean, do those
You
look?
look over there. It's red.
We already know
Oh,
those slopes. Those slopes are the same. So, I mean, suspiciously, I guess they might not be.
Purple to orange.
Yeah. So we probably have to do 3. If we did 3 of them, we could pretty. All right. So let's do purple to orange. So purple to orange. So I'm gonna do quick the distance formula. So d for distance equals the square root of
We don't need.
the x's. That would be -4 squared plus the y's. 2 squared is, correct me if I'm wrong. That's 16 plus 4, 20, square root 20. So 2 root 10, right? Is that right?
Yeah.
And then what was the next one I was going to do?
Orange and green.
Hey, what did I do? 2 or 5?
5 times
Purple
4.
and green.
Thank you. What are we doing?
That'd be 5.
That's a
Yeah.
4.
And I wrote a 4. I heard exactly what you said and I wrote a 4. What are we doing? Purple. We just did purple orange, so now we need to do purple green. Purple green. So this minus this squared, that's 4. Is that right? Now I'm doing 2 things at once. This minus this squared would be 4, right?
Right.
Plus this minus this would be 16. That's 20. All right. Yeah, wrongs.
Oh, it is.
Yeah, we got
Yeah, it is.
square root 20.
Oh.
Now,
If it's parallelogram.
well, we knew it was a
It's a
parallel. That was the
parallelogram.
first thing we did. We did the slopes. Now, granted, we really would have to do it to all 4 sides to confirm, but I mean, I'm doing it. I mean, I did it on Desmos, and you can by observation. By observation is not allowed in geometry, but
Wait
I did it anyway. And the book says that this is 16, right? Yeah, it's a rhombus. All right.
Jack, we did 1 through 10 and then 15 through 18.
Yeah, we have these things called classes every day, Jack.
You don't even know it. You don't.
All right.
You're supposed
Yes,
to
you-
watch the
you
video.
should.
You have to check the box that you watched the video.
Yes, exactly.
So you're lying if you checked it.
You watched the
So
first
after you
part.
did
You watch the first part and you're like, oh yeah, parallelograms. I'm not parallel angles. Well, I don't know what I said.
We got you. All right. Any other questions
What is life?
on the map?
Oh. What is life according to math? What is the square root of a number divisible by x?
Which one is that?
Remember that?
Of a number, any number, so it's just the square root of any number.
But it's divisible by x.
Yep.
Well, you got to tell me a little bit more about
Tell me
X.
what x is.
All right, x is a number on a graph.
Okay, then it's any number.
All right,
Well,
but
it
you can't-
could be undefined if that number is a negative.
exactly. Therefore, yeah.
So it's any number. Because
No.
undefined is actually infinity.
All right then. How about that same equation I have said plus the square root of the exact same number.
All right,
divided by the
let's do
divisible
some actual math. There's no questions. I'm just going to collect for this particular one. So remind me to collect at the end, because today we're doing something. All right, up to this point, I probably would bet that there's not a single thing that you haven't seen at least once or twice. Today, different stories. You've never seen this before. You might have heard about it in physics class in 8th grade last year, but you haven't done this before. I remember doing this in algebra too. I don't remember doing it in geometry, but it fits in geometry as well too. So it's a worthwhile thing. I don't think I've ever seen this on SAT or anything like that. So why do it? Well, you will be doing this in physics. That's in what, 2 years? You do chemistry next year and then physics. So you will be doing this. Let's see, what does it look like? Hey, next Monday we will not have class, field day. Remember, periods 1 through 4 you're going to have, but then 5, 6, 7, 8, we'll go into the park, eat lunch, and play reindeer games.
Yay.
We'll have a quiz on this Thursday. More about that I'll start talking about tomorrow. And notice 3 weeks and we're already in semester final review. That final week there, which
So
isn't shown
we're
right
never
here.
gonna get into chapter 14.
Well,
We got 14.1.
But what if there's a snow day, sir?
maybe we won't get to chapter 14.
What's chapter 14?
All right, so it gets filled up. I might literally not do 14.1, but just might jump right to dilations. That would be the one thing that you might not know how to do. Although after today's class, there's some commonality between what we do today and dilations. All right, so here we go. There's a lot of stuff here. It ain't as bad as it looks right there. I mean, it's not an hour's worth of homework. Most of these are done very quickly, but you do have to graph.
Baloney.
And don't assume you know what you're doing until you get at least a couple examples.
I assume everything, so dang it. I'm joking.
I know how you
In
do it.
physics class, you do a lot of really cool stuff with this.
Do a lot of cool stuff now. I can throw this book into the air like that.
You are so unlike your brother. Your brother has literally said 10 words in a year in my class.
He's just shy. He doesn't like the big humans.
Define the big human, McKinley.
The eighth
Technically,
graders.
you could be a big human.
Yeah, you're a
Yeah.
pretty big human to him. Although I did notice he's starting to grow now. Because he was really short at the start of the year.
How dare you?
Oh,
Dan, you were pretty short 2 years ago.
Yeah, I'm still short.
No, you're taller than me now.
Yes.
Stand up. I think you're taller than me. Well, close.
I know I'm taller than you.
Yes, you are taller than me.
Not like 2.
All right, here we go.
No, like
Vectors.
70 feet.
Vectors. New thing. Do you remember vectors 8th grade?
Yes.
I remember.
What do you remember about a vector?
They're annoying and they're also very simple once you get used to them.
I remember the word.
Right. That was kind of all I did too as well. Vectors. Jack, do you remember anything?
No.
Do you remember the word?
Yeah.
Okay.
And magnitude.
Very good. But did you get that from the book or did you get that from your
Wasn't
brain?
in the book.
All right.
Oh yeah, it's right there.
You found it pretty quick, didn't you?
But magnitude is something absolutely that goes along
here,
with
one second.
vectors.
Let me look for the bold word. real quick. Oh, there it is.
So depending upon, obviously you guys all have Mr. Surratt, but I made this class just, depending upon who teaches you 8th grade science. But sometimes they cover vectors, sometimes they don't. The vectors is a pretty high level math, as you'll see when you take physics class, or you get to college and take calculus-based physics. Oh boy, will you be doing some vectors. So vectors, it's a pretty easy concept of knowing what it describes, what it means. It can get really detailed, really detailed. What we're about to do, we're going to be doing the easiest of the easy part of vectors. Very useful later on when you get to your physics class. Tons of new vocabulary, words, and procedures today. Make sure you take really good notes because it can become a little bit confusing. All right, so here we go. Generally speaking, vectors are applied to motion. So anything in motion or anything put into motion can be described with this thing called a vector. So motion, as you learn in science class, we talk about force, mass, and acceleration, right? Force, mass, and acceleration, the relationship between those three. The famous formula from
Dirt.
No.
Equals
You said
squared.
force
E
F
equals
for force.
F equals mass
A.
squared over acceleration.
No.
Mass times A.
Mass times A. Look at McKinley. All right.
That's what I literally said.
So,
Ma.
so if you, what it describes is how something gets into motion, right? That motion itself is a relationship between the amount of force that you apply onto the object and how quickly you accelerate it, right? So if you want to make this marker here go really fast, you have to accelerate it very quickly. If you want to make it go slow, you accelerate it very slowly. The amount of force to take it slowly is different as opposed to making it go 100 miles an hour, right? And that's kind of a relationship. So mathematicians a long time ago and physicists wanted to somehow use the tools of geometry to help them with this problem of motion. And they came up with this thing called vectors. Motion itself is not just a one-dimensional thing. Motion itself has both a force and a direction. So if I want this to go in that direction over there, I have to literally force it in that direction as opposed to force in that direction. However, the amount of force I apply on it could go in either direction. I could put an amount of force, newtons, right? Amount of newtons and it goes in that direction, or I can apply the same amount of newtons in that direction. So somehow in the math, we have to be able to describe both the amount of force we apply on an object and the direction that we make it go. Okay. All right. They use the word magnitude or intensity to describe the amount of force that's applied to an object. All right. So here come the definitions. All right. In box one, vector. So a vector is a quantity. Quantity means there's going to be numbers involved. It's a quantity that has both a magnitude and a direction. And if you want to think about this thing as things in motion, the magnitude is how much force you're putting on an object. And obviously the direction is the direction that you're trying to make it go. So vectors are going to have, till you get to college, and you have 3 dimensions, but for 2 dimensions, right? Vectors are going to have 2 numbers.
Well, it's a good thing I live in the 4th dimension, but you guys
Okay, Thanos.
Thanos. What?
Nana.
Have you ever seen the movie?
No.
Hey, but didn't you have a whole slide about it on 7th grade? I thought you.
Yeah, I did. I just picked out whatever was the most popular movie for that day. In fact, I literally had that class the other day. I was like, oh, I got to update my slides.
Yeah, now
What did I put?
Now it's Black Widow.
No, I put
King
some
Kong
other.
versus Godzilla.
The problem is that, yes, that's exactly what I put.
Snyder Cut. Snyder Cut.
No, I put Godzilla
No,
and
Snyder
King
Cut's
Kong.
better than Godzilla.
Actually, there's not many movies out
The
right now.
Snyder Cut is better than Godzilla.
Yes, but you don't tell that to a bunch of 7th graders like, watch this R-rated superhero movie. You'll love it.
All right. Vectors, we will be drawing on the coordinate plane. So we're going to draw these vectors on the coordinate plane. Now, we got to be very careful. Up until now, when we draw something on the coordinate plane, we're showing a location. You notice, do you see the word location anywhere in the definition? It says direction, but it doesn't say location.
Directions have to have a location, otherwise
Right.
they cannot go in that direction.
Have to have a starting point,
And the
right?
starting point must be in a certain location.
It does.
Therefore,
I'm
there
gonna-
is location in the
I'm going to
given
tell you,
direction.
and that's the first thing you got to wrap your head around, is that when we draw these vectors, we're not describing it being in quadrant 1, quadrant 2, quadrant 3, quadrant 4. Even though it might appear to be that way, and we will use the information from the coordinate plane, we're not literally saying this is where this vector lives. We are putting the vector on the coordinate plane, but it's not describing the location. So vectors are drawn on the coordinate plane, but we don't use it to find a location. All right, so vectors are not locations. They're magnitude and direction. All right, so in geometry, vectors are drawn. Here comes the pain. You ready? So everything on the slide right now. Vectors are drawn as rays. Like on the graph, you're going to draw a ray. And that's where the similarity with math ends. Rays go on in one direction forever, never stop. Vectors don't. Even though it's going to have an arrowhead, it doesn't mean it continues. And it'll make more sense when we do a couple examples. Secondly, this is the symbol for vector. You see it's different than ray. It's only got half of an arrowhead. And it goes on the top. It still points to the right, just like rays do. It's still going to have two letters. It's going to have two letters, and it's going to have a vector symbol over the top of it. When you look at that, that's what's supposed to tell you, hey, look, I got a vector.
Haven't had coordinates in a while, the lines over their coordinates thing, whatever they're called.
So we read this as vector AB, not as ray AB, because it's not a ray symbol. All right, I'm warning, it's going to get complicated now. So rays have no length, right? Turns out the vectors, as it's drawn on the coordinate plane, will have a length. We will actually, tonight for homework, calculate that length. Except the length of the vector is actually its magnitude. It's showing you how much force is being applied. You have a long ray, and I'm putting air quotes there. When you have a long ray, it means you got a lot of force. When you got a short ray, it means you got a little tiny bit of force. The longer the ray, the more force you're putting on the object. So it says length of ray, question mark, because rays don't or have infinite length. When we draw the symbol for vector on the coordinate plane, we use an actual ray symbol. When we draw the symbol for it, we don't draw the symbol for it, we draw like half of a ray. What you draw on the coordinate plane tonight will have everything. It's going to have its direction, and it's going to have its magnitude. All right, we have another symbol for how much force you're putting into an object. Now, I keep saying force, it can apply to other things. When you see those absolute bar symbols, it doesn't mean absolute value. It means what is its magnitude. You see these absolute value symbols, it's asking you to say what's the magnitude of your vector. And remember, once again, am I kicking the football hard or am I kicking it soft?
Medium.
If you see the absolute value symbols, it's asking you, how hard are you kicking the ball?
6,000 miles into the stratosphere.
That would be a very long ray to draw on a coordinate plane.
Now, if I put
Be a
the
very strong
coordinate
line.
plane into millions,
You would actually have to change some units there in order to make that thing fit.
well, I could make it like 6,000 to.
Agree, but the key takeaway here is if you see a little short ray, and remember we're talking vectors now, not actual rays, you see a little short one, the magnitude is very small. You see a very long one, magnitude is large. The length of the ray as it's drawn is its magnitude. So when you if you're looking at the book right now, when you see the little arrow, the length of that arrow from where it starts to where it finishes is its magnitude. You're going to use the distance formula. And that's going to be its magnitude. So you're going to use the distance formula to do the calculation. They're going to ask you, what's the magnitude of the vector? Well, you're going to have to use the distance formula. Where the ray is pointed is its direction. Like, where is it going? Now, obviously, we're doing this in 2 dimensions. So if you restrict yourself to a 2-dimensional surface, it makes a whole lot of sense. Vectors can be in 3 dimensions as well, too. But where it is pointed is the direction of the force, not the force, but the direction of the force. If it's pointed up, well, you're kicking something straight up. It's pointed to the right, you're kicking it to the right. Good, everybody? Okay, now here's the complication. This is going to look like an ordered pair. If you want to know the direction, where it's going, you write the direction as an ordered pair. And it says the change in X or the change in Y. Guess what that sounds a whole lot like? Sure, it sounds like slope. Is it the slope formula?
No.
It's backwards, right? Change in Y over change in. And by the way, it's not a fraction, it's an ordered pair. It literally is an ordered pair. So if you want to know which way is the ball being kicked, you look at this ordered pair, and the first number is how far it's going left or right, and the second number is how far it's going up and down. And I don't mean distance. I mean, the way that the arrow is facing on the coordinate plane is where the force is being applied. Okay, if I put the force directly to the east, or west in your case, as you're looking at me, if I put it that way, then I'm going to have no change in y, but I will have a change in x. And it will be in a negative direction, by the way. And you're like, well, I'm going to have to see this to understand this. And we'll do enough examples. That's a pretty busy slide, but this is the complication of vectors on day one. You do this all the time, it's no big deal. We okay?
It becomes numb.
All right. It's not the slope. It certainly looks like the slope. It's just not the slope. All right. Complicated, probably, but it is easy. All right, so let's do some examples. So the book's going to ask you 3 questions. It's going to say, sketch the vector. That means literally put it on the graph.
Yeah.
It's going to say, where is the force being applied? What's the direction? You're going to get that from not the slope, but that ordered pair. And then lastly, they're going to say, well, how much force is being applied? That's the magnitude. We're going to use the distance formula. Okay. And I'm going to do them in this specific order. You'll see why in a second. It makes sense to do it in this order. All right. So that's easy. That's easy. This will be the Pythagorean theorem, right? The distance form. Remember, that's where the distance form comes from, Pythagorean theorem. Okay. So this is box 2. We'll take some time. We'll do this one together. So it says, sketch the vector, find the vector. That's the hardest thing. When they say find the vector, what they're asking you is, where is it pointed? Like, where is it going? And lastly, calculate its magnitude. I don't like this find the vector. It's where kids usually get lost. But it simply just means, what's the direction of the vector? Why don't they just say, what's the direction of the vector? They don't. They say, find the vector.
Going backwards.
They're going to give you literally 2 points. The 2 points. The first one, well, you can tell. The first letter is where the vector starts. The last letter is where the vector ends. Remember, it's arrayed, but it doesn't go on forever. So the first one I said, it's easy. They just want you to graph these 2 points. You got to do them in a specific order. It's got to go P then Q. So you go from P to Q, and you put an arrow on the end of Q. Okay, sketch the vector. It's not that complicated. I need a point at -5, 4, and it's going to Q. I don't know if you can see it, but there's an arrowhead right there. If that were a ray, the ray would go on forever, wouldn't stop. But it's a vector, so it stops right there. And it has to stop. You don't get the option. It has to stop at 1, 2. Well, remember, the direction is where the force is going. So in other words, if this is my ball right here, and that's the vector of force, where is this ball going to wind up? It's going to wind up, over here when you kick it. The length of it represents how hard you're kicking it.
Okay, so it's going.
You're like, well, usually a kid says, well, what about gravity? Oh, yeah, you're right. What about gravity? Wait till you get to college.
College.
Oh, boy.
Oh.
You will be doing the impact of multiple vectors on an object.
What if I don't want to go to college?
Yeah,
What if you
Well, I think your parents are going to have something to say about that.
What if you go to a college that doesn't teach you about math?
Then you won't be doing vectors. Right? But if you do anything where you're taking, typically you take physics your first semester. If you're doing, unless you're doing, I don't know, a sociology degree or something like that. But if you're taking anything in the STEM field, semester 1 is Calc 1, Physics 1, and then the rest is, whatever else if you're doing computer science and the computer science part. But Calc 1, Physics 1, unless you take the AP test and you get out. Then instead of taking Calc 1, you take Calc 2. If you take AP Physics, instead of taking Physics 1, you take Physics 2. Okay, so easy, hard, what? Ridiculously easy, right? Find the vector, really poorly titled. It's asking you what is the direction that it's going. And we said it's not the slope, but it certainly looks and sounds like the slope. It's basically an ordered pair where the first one is your change in X and your second one is your change in Y. So how do you find that? You literally look and you just do the change in X. I'm going from P to Q, so what's my change in X?
Negative.
So to go from here to here, I'm going in the negative direction.
No, positive.
Well, how many squares?
Oh, squares.
And remember, we're talking about the X's. So what's my change in x? Well, I'm going in that direction.
Well, don't you just count up and then down?
You do. So what's the count?
Well, count from
She's saying 6. You agree or disagree?
6.
Is there a better way of doing that rather than counting squares you can't see?
Subtract
Subtract what?
the x's.
Subtract the x's. -5 minus 1. But remember, we're going in that direction over there. So it's really 1 minus 5. Otherwise, we would get a negative number. Yeah, you get why we did that?
-5.
Do you get why we did that?
It's 1 minus -5.
So you want to take always your farthest right, subtract your
It's
farthest
not
left.
1 minus 5.
1 minus -5.
You said 1 minus 5.
Okay, I meant 1 minus -5.
That would be -4.
That's my change in x. Now, you could have gotten that by counting squares. What's my change in y?
2 minus 4.
-2. So that right there is how you write what is the, you found the vector. That's the vector. The
Right.
vector is 6, -2.
Now I have to calculate the magnitude. Great.
And that wasn't hard. Now, like I said, since you did it in this order, I mean, you could do the math. The math isn't that bad here, but if it was really weird numbers, which it could be in physics, well, you know, you got to use the math. But if it's not really weird numbers, you can count squares. It's your choice. All right, so the last one, which is, it's not too impossible. Remember, it's going to have these absolute value symbols right here, and it's going to ask you to calculate the length of the vector. In other words, how far is it from P to Q? It's just the distance formula. All right, well, here are my values. So who's got the distance formula off the top of their head?
Square root of x1, x2 minus.
Do it, no, plug in the numbers.
So the square root of,
1 minus 5.
yeah, so it's
Square.
6 squared, so it's 36
Plus,
plus 2 minus 4, which is -2 squared is 4.
okay, so we got what, 16 plus 4, is that right?
36 plus 4.
Oh, 36 plus 4 is
So it's
40.
Square root
Okay.
of 40.
And that would be 2 root,
2 root 10.
that's why I was thinking earlier, the root 10. All right, so 2 root 10. Anybody want to make a comment?
No.
No.
No, look at the board. Anybody want to make a comment?
Hey, that might be the magnitude.
No, but true, but I'm saying, anybody want to make a comment?
No.
Keep implying that.
Anybody want to make a comment?
Oh.
Now you're just making me look dumb.
Yeah.
Well, wait a minute.
Wait,
If
Oh,
you
okay. I get it.
take-
So you just square root both of them. So you just take the square.
Thank you.
So you square that.
I wasn't
I
looking
was
at
worried. So what was his comment?
Yeah, you
7
just
is not a
square
prime
the-
number.
You just square what?
The
And what is that?
The
prime
direction.
You
number.
just square root the, or square root. You just square the direction if you want to save yourself some time. And remember, I started by saying, hey, I'm going to give you to these in a specific order. I don't care what the directions say. If you want to make your life easy, sketch it, because your sketching it will allow you to either count squares if you choose to, or use the Pythagorean theorem. And then if you find the direction second, well, then you can find the magnitude like that. Okay, so that was the notice. And thank God I didn't have to call the slide up and make it very large for you. All right. Let's do another one together. Here we go. Did I give you a graph or did I give you a graph on this?
Yeah, you did.
I did? Okay, good.
If you didn't, then that would be bad.
All right, step number 1, sketch the graph. The only way you screw this up is if you don't put the right point first. So the right point first is the P, 2, 2. Q is 6, 5. So we go from 2, 2 to 6, 5. We label it correctly. Step number 2, find the vector. The find the vector is the change in x over the change in y. I mean, I can do this really quickly with the squares. We got 1, 2, 3, 4, and then what, up 3 or 4? Up 3. So 4 thirds
4 thirds.
or 4 3, I should
So
say.
16 plus 9 squared of 16 plus 9.
And then, since we know that pattern really quickly, define its magnitude. It's the square root of those squared,
So square root of 25.
which is
5.
5. Okay. All right, who's lost? That's a lot of stuff. If this was not an honors class, I'd probably do about 5 of these, and you get very bored very quickly. Remember, I will post the videos, so if you get home, and it happened to me, I remember having this class in high school geometry, and like, oh, this is easy, and then I got home, and I'm like, wait, I've forgotten everything, and maybe hear it a second time. It is easy stuff, but you can forget it because it's something you've never done before. All right, so we have a graph of the. Now, I just want to point out, the vector doesn't physically live here. I can move it down here, and I would literally get the same answers, right? Where it started, or where it started, the P and Q could literally have been drawn anywhere on the graph. Just because I started at 2, 2, if it has this direction and this magnitude, it would look exactly the same, and we would get exactly the same answer no matter where we put the vector. And that's the part about this isn't literally where it lives. Maybe it lives over here. We just chose to start at 2, 2. All right, try to do this third one all by yourself, and then I'll review the answers.
Well, what if the shrimp finally uprise against that?
Well, then I'm not going to be eating shrimp scampi on Saturday.
Ironic. Well, what if the shrimp are good?
I died in some.
That was me too, Ben.
No, you don't get to die. So.
Why are you only allowed to die on the inside?
Because when one has to go through torment after torment after torment to understand the physical value of pain, then they don't really understand. They don't really have to feel it ever again, except when they experience a new type of pain, which they have to go over and over.
Well, that's kind of like life.
Again.
I think you should get used to that, Ben.
Who's been to the DMV yet?
What's
Was
that?
it painful?
Yes.
I don't know. That's why all adults talk about it.
What's the DMV?
It's where you get your license.
You have to wait for like 15 hours.
It wasn't
Exactly.
15 hours, but it wasn't fun either.
It feels so much
In
longer when you're there.
In a non-COVID environment, when you walk in, they have the infamous, you grab a ticket and, it says 48 on it. And then you look, you see they're on number 2. And then you wait 15 minutes and then they call number 3. And you're like, oh, dear Lord, I'm going to be here all day.
Well, it's simple. If it takes you approximately 15 minutes to go through one answer, and then you know that it's on number 2, and it's
No.
That's
I
taking
do the
10
math.
hours.
45 times 15.
Well,
You do
but
the,
you can't do that because
45 times 15 gives us an answer of 675. Take that divided by 60, 11.25 roughly hours, approximately 11 hours.
You can't do
Yeah,
that though
you
because
could've
not
figured that out
everyone's
with
there for the
11.25.
same thing, so it'll take
that's
different
right.
amounts
Some are
of time.
shorter, some are longer.
Thank you for that.
Some people
No
live there
problem.
for like license plates.
All right. Well, the sketch is pretty simple, but who's got the vector itself? What's the vector?
7.
Vector's going to be 2 numbers. It's going to be an order pair.
Negative.
2.
5, -2.
Aha!
All
Not
right.
negative.
5, -2. Very good.
She said 1 negative 2.
Yeah, because I added it wrong.
I got
Yeah, it
negative.
can happen.
Wait, I got negative 5 too.
How'd you get negative 5?
It doesn't matter. It's squared anyways, but
Well,
Because
yeah,
I
but
went-
it does matter
I
for the vector
I
itself.
went from Q to P.
Well, that happens. We're going to give a name to that here in another couple slides.
Oh, got it.
And that would not be the same vector. That'd be the vector of kicking it backwards
It'd be the same
in the
magnitude.
opposite direction.
It'd be the same magnitude.
Guess what we're going to call it?
It'd be the same magnitude.
Guess what we're going to call
It'd be
it?
the same magnitude.
Guess what we're going to call it?
Guess what we're gonna call
Reverse vectors.
Close.
it? Ooh, we're
Opposite, opposite,
We're going to
opposite.
call it opposite vectors. All right.
Why do I want to do an opposite vector? What's the magic in that?
If you want to talk about positions, right, and you want the object to return back to its starting location, then you need to apply an opposite vector.
Oh God.
If you want the thing not to move, then you need to do opposite vectors.
Well, I can make it not move.
If there's any force being applied to something, it's going to move unless you apply an opposite force. Like right now, this is a pretty weak idea, but the floor is an opposite vector to gravity. It's not a perfect analogy, but it's close, right? Because the floor isn't pushing upwards. The floor is resisting our movement. But that opposite vector will hold true until I weigh, 40,000 pounds, and then the floor will give away. All right. I don't know if that's the exact thing. What was the magnitude?
Square root of
A
29.
number.
25 plus 4, so 29. There you go. Square root of 29. Very good. Okay. Next concept. What would happen if I took this vector right here and I doubled it?
Because
Like I applied twice the force.
well, there'd be two vectors that equal one vector because you have the arrow, but then it continues on
No,
because
it would
there's
just
two
be one
arrows.
vector that's bigger.
And would it still go in the same direction?
Yes.
Yeah.
But it would be
Bigger, twice as bigger.
twice as big.
Right.
All right. Not a hard concept to understand, but you can put a number in front of a vector symbol and it literally means double the vector.
Put a dot at the half point of your reverse vectors or opposite vector.
All right. So even before, if I'm claiming that this is a double vector of this, even before I even look at this, take a guess what's going to do that.
It's gonna 6 4.
Triple.
Gonna double.
It's just going to double it. It's literally just going to double it.
Whoa.
So we don't even need this if it has tonight's for homework. It's going to ask you to do some sort of multiplication to it. So that's what's happening. All you're going to do is take your vector. Remember, find the vector. If you're going to double it or times by 1.5 or something like that, you just take those numbers and you do the scalar multiplication of that. So that's called a scalar multiple, and it increases the vector by size of k. So they will give you a vector, right? Ordered pair, it looks like. We will attach some sort of scalar to it, and all it does is attach that whatever's on the outside to every number on the inside of the parentheses. And remember, those numbers on the parentheses describe the change in x and the change in y. Kakabi.
It's pronounced kebab.
I don't know.
Bye-bye. Bye-bye. Goodbye-bye. Goodbye-bye.
We know that Anna heard baby.
What's going to happen if k is negative?
How dare you insult Anna?
It's negative.
You should be more respectful.
And negative.
Didn't you insult her today too?
So if k is negative, stay with me. If k is negative, then it's straight at the same math. You're just going to be multiplying with a negative. What is the result of it? The vector will still start at that same place. It will just be, as we described before, opposite. It'll go in the opposite direction, but it will be the same length.
So it really is if you put a dot at the half point of the double scale.
And that would be the same as multiplied by half. Yeah. If you put a dot in the middle.
Right, and if you put a dot in the middle of a vector that's been multiplied by 2, then it would be 2 reverse vectors.
As long as you rewrite it to show that the second one is going in the opposite direction. Otherwise, it looks like this and then this added together. Because you got to flip the other one around.
Right, yeah.
There used to be a really simple computer game where you were trying to blow something up, and they would you had to type in numbers for force of how far it threw something, and it was basically a vector game. All right, look at those three. Those are all vectors, by the way. Guess what I'm going to describe?
The relationship.
Okay, what do you think the relationship is?
Parallel.
All of them?
No, well, I mean, maybe.
Technically,
Actually, yes, they are all.
Technically,
They are all parallel.
they
Yeah.
all have the same slope.
They all have a slope
from what I'm seeing here.
You're going to claim
They're all
that this
parallel.
one is parallel to that one?
Yeah.
Why?
No, it's the same line. If you were using lines, it's
What did we say about
Vectors don't go
vectors?
on infinitely.
So
even though they're two
therefore,
separate lines, they're
guess
still
what we can
parallel.
say
it is parallel.
about vectors if
Any
they
vec-
are
Same slope.
If they're
if they have the same
if
slope.
they're the same slope and they're not touching, actually, never mind. If they're the same slope, they're
We don't even care about the touching
and
part.
not and not overlapping. They can't overlap.
We actually just say if they have the same slopes, they're parallel. So all, and this is just a big thing, everyone would agree that, but it turns out that all vectors that have the same slope are parallel. And we don't, although we're going to use the word slope, the correct word would be direction. They all have the same direction and they are parallel. Now, there's one other thing, there's a big or here. What else does it say?
Opposite.
It says opposite. So the thing that we've been describing, opposite vectors are also parallel vectors.
Right, but the
So it
slope
turns
is
out
still-
all four of those are parallel.
I mean, the slope is still the same. It's just -1 over -1.
Right. And the hardest thing tonight for homework is going to be, they're going to give you a slope that's going to be opposite, not opposite reciprocal, but it's going to be opposite. And you have to recognize that it's also parallel. Yes, you will calculate, I mean, straight up slope. They're going to give you 2 points on the vector. calculate its slope, and if it's the same or the opposite, then you conclude that they are parallel. And I got to start talking faster because we got 2 minutes and I got one more concept.
Well, technically, we're gonna stay in this classroom.
Yeah, we're gonna say
For
that.
Oh, then I can slow down then. Well, what about my 7th graders? They're not coming back?
They don't deserve.
They have
to be
No,
CMAS.
here.
I think we're both. I don't. Miss Nichols just told us.
Wait, no, we're not gonna.
All right. You guys will have a thing. Okay, we got to talk about perpendicular vectors. These are vectors whose direction is 90-degree different from the other, as the name would imply.
Right.
Once again, from the previous class, remember slopes that are opposite reciprocals of one another are perpendicular. It's going to be the same thing for vectors. So when you calculate the slopes, if they're opposite reciprocals, if they're opposite, they're parallel.
But there's really nothing different. It's just.
But if they're
segments.
opposite reciprocals, they're perpendicular.
There's really nothing different in lines. It's just segments, pretty much.
Well, just remember, for it to be parallel, not only the slopes have to be the same, the y-intercepts have to be different. Otherwise, they intersect because they go on forever.
Right. I'm just saying.
Not true for vectors.
Why does this need to be stated at some?
Right. Well, this is just a natural conclusion from that. We haven't figured out, are the 7th graders coming in or no?
I think they are, but I was thinking of sending them out to the gym.
Okay,
Because they're gonna see us all day.
cool. Perpendicular vectors. Yes?
Yep.
A natural conclusion from the fact you understand what perpendicular lines are. All right. Equal vectors. Well, clearly those are vectors who both the magnitude and direction have to be the same. They can be parallel, right? If they have the same slopes, but if they're equal vectors, they have to point in the same direction and they have to have the same magnitude. So tonight for homework, when it says, are they equal? You got to do 2 calculations. You got to calculate the distance, and then you have to calculate their direction. And remember, we get their direction from that ordered pair, the change in x and the change in y.
Which ones are going to ask if they're equal?
Mm,
Not getting it all.
Well,
No,
there are
there is
headphones in
headphones
there,
in
but
there.
they totally just pull them out. Why not?
all right, I have to look through that one.
Also, for numbers 20 through 25, adding.
Yeah, that's the part I want to get to.
All right, then get to it, please.
Vector sum.
You want me to skip this one, the parallel part?
Yes.
No.
All right, how do you know if something's parallel?
Oh, they have the
Opposite
same.
reciprocals.
If they have.
Opposite or same slopes, right? Opposite or same slopes. Okay, so you're just going to do, the rise over run. Are 7th graders coming in or no?
They're still testing.
Okay, cool.
I told her when she was done, she could release them like that. I think she can swim to the gym.
Okay, back up here. So PQ, all I'm doing is taking, where's Q? There's PQ. Oh, PQ's right here, 9, 6. 9, -6. The one thing you're going to screw up is the fact that, remember, it's written change in x, change in y, and then slope is change in y over change in x. So you can really mess that one up. So it's -6 over 9 reduced -2/3. We do this one. Remember, it's opposite, so it'll be 4 over -6. Does that reduce to -2/3?
Yep.
It does. If it had reduced to what, a +3 over 2, then it would be perpendicular, opposite reciprocals. But in this case, we get exactly the same number, or it's opposite. So if we had gotten a +2/3, it still would be parallel. That's the tricky part. Is it can be the same. To be parallel, or it could be opposite. Not opposite reciprocals, that's perpendicular. Hopefully that made sense. All right, perpendicular. Last idea, vector addition. Okay, here's the idea. This is a pretty cool thing. They should show this in physics class. If I want, imagine a flat surface and this is a ball and I roll it, right? I want it to go to McKinley. So which direction do I throw it?
Towards it.
Turns out you don't have to throw it towards him.
You
I
can
can
throw it to
throw
me.
I can throw it to the wall,
I want to throw it to me.
Oh yeah, you can throw it to the wall and it'll bounce to it.
because what it's going to happen is when it hits the wall, another force will be applied onto it in an opposite direction and actually could hit him. So what we're doing is we're doing two vectors there.
Wait,
Yeah,
sorry,
the easiest way to get it to McKinley is just push it in that direction. But I can apply 1, 2, 3, 4 vectors to any object to make it go in any direction. So check this out. If I make an object and I push it in this direction, ignore gravity, right? Ignore friction, and I push it in this direction, at the same time, Anna is standing right here and she shoves my shoulders in this direction. Guess which direction I actually go in,
Towards him.
right? I'm walking in this direction, but Anna just pushed my shoulder and she shoved me in this direction.
It depends on
Ignore
how-
friction, ignore gravity.
It depends on how.
Whoa, no
how
gravity.
And it
strong
does.
shove.
If there
It
was no
does.
gravity, float on infinitely.
Agreed.
Sure.
But I would actually move. I'm walking forward, but she pushed me this way. This is what actually happens in space. I would travel in that direction. That's what it's showing you right here. The red line is what's called the resultant vector. The red line is not where you pushed it. I pushed it in this direction, and then I also this isn't time, so it wasn't like I pushed it for a certain amount of time and then I changed the direction. These are things that are happening exactly the same amount at the same time. So I'm pushing it in this direction and I'm pushing this direction. The resultant vector is this red solid line right there. So what basically you do to do this calculation, it's called vector addition, is we take the two vectors, we are literally just going to add them together, and the resultant ends up being this red solid line. Pretty nifty. And when it says addition, it literally means you just take it and you add it. Okay? So all I do is I take PQ, add it to QR, and the resultant is PR. What does that mean in numbers? Literally as simple as you think it would be. So guess what the answer is?
Is
6, 4.
And it literally is that simple.
okay. That's
Wow,
easy.
that's easy, yeah.
It's very easy.
And it's a pretty, by the way, this is Newton, came up with all this in Galileo. It's a pretty nifty thing. The hardest thing for you to wrap your head around is it implies that, well, something happens and then something else happens. Both of those can happen at exactly the same time. Oh, there could be a delay too, right? The problem is with the delay, if Anna waits to push me until I get right here,
It's already gonna be.
I don't wind up there, I wind up over there.
Yeah.
So both of these are happening at exactly the same time. And that's how it's drawn, by the way. And in physics class, in 2 years, you're gonna do a bunch of those, bunches of those. Cool, pretty simple. All right, so vector addition, the resultant vector, that's the, what happens as a result of the other two vectors, is when two or more, and there can be lots of these, are combined. Two or more of the vectors are combined. It's harder to write the definition than it is to actually do the math, because the math is literally, I believe you're going to the gym.
Okay, thank you.
Danny, you already done the homework or
Part of it.
part? Okay.
I'm checking something.
Is there anything I left off?
No.
Okay.
What is that? Are you dying or anything?
Uh, 26 looks like this. There's one vector.
Whoa.
There's
We're
another
not doing
vector.
26.
I know.
We
Oh,
are.
we are doing 26.
Guess what the resultant vector, look at this. Guess what the resultant vector would look like? Where would it go?
It would go. It would
Space.
just be between those. Well,
This is my starting point, by the way. And these are my two vectors that I apply to. So guess where the ball would go?
just through the middle. It'd be a bisector.
Well, I'm trying to push it this way, but I'm also putting this way. So even though it's trying to go in this direction, this one's pushing in that direction. So it winds up going something like that.
Yeah, it makes those weird things we did in chapter 3. Remember?
Angle bisectors?
Yeah.
Okay.
Those weird things.
And those weren't weird.
Those weird
You thought those were weird. We're gonna have big problems. All right. So the idea here is they'll give you two vectors. You simply take them and you add them, and it's not that complicated. I mean, it literally isn't. Occasionally they might. I'm looking at homework. They might throw a scalar in there as well too, but it doesn't look like it. 31. We didn't have 31. 31 throws a scalar.
So we're just 1 through 26.
Is that what I assigned?
Yeah.
And 26 is exactly like what you'll do in physics 2 years.
Why do you need algebra to prove that? 31. That just seems like a obvious, it's just distributed.
It's
property.
distributed property, right?
It's just, that seems
There,
so
there's,
obvious.
there's not even that much of a proof there.
Why is that in the B
I
section?
don't know. Because it has no, all letters and there's no numbers there and they figure kids will freak out. All right, that was it. It was only took me an extra 10 minutes. What do you know? What number are you on now, Ben?
18.
All right, well, apparently it's gonna take you a bit longer than you think.
Did you send him down to the gym?
I did.
Like, where is he? Been like 6 years.
Homework.
Thank you.
Yeah, homework.
You want to do 18 in class?
Sure.
Okay, this one?
Is it, how long have you been stuck on it?
I just got to it, but I'm getting a headache, so I don't want to do it.
See,
What's up?
can I have a worksheet for 7A, but homework worksheet?
can't figure it out.
I
For
have a
what?
headache and brain
The math
headache.
homework for 7A, the worksheet.
Which 7A? We're not on chapter 7, we're on chapter,
Oh, because
12.
today for homework, everyone got like a worksheet.
oh, that worksheet. Yeah,
Yeah.
yeah. I was gonna say, we're not on chapter, we're on chapter 12. How did you not get one?
I don't know.
Somebody kept it rather than giving it
I
to
bet
you.
it's Felicity.
You can't trust her. Don't tell her I said that,
Okay,
because I'm joking.
okay,
She's very trustworthy.
okay. Thank you.
Never mind, don't do 18 in class. Do 26 in class.
26 is just an explanation of what I literally just threw up there.
You guys are so lucky. You don't only have like 5 people to talk to.
Yeah, that's the problem.
Yeah, but classroom like is 26
But you
people,
guys
so
are gonna
like-
have an extra. Gaddison,
Isaiah, Eliza,
Alex.
Alex.
and then
That, the
4
shadow kid.
girls,
Some of them
and
are
then
coming
there's,
back.
I think, 2 or 3 new people. I mean, you're gonna have a big class next year.
Only
No!
2 of the girls who were
It's
taking
wrong.
geometry though are actually coming
They're
to
coming
school
back.
next year.
We go from 6 to what? 20?
It's not gonna be 20, but it's gonna be in the teens.
17?
No, it'll probably be low.
14?
It'll easily
It'll
be
be
triple.
like 7th grade.
You need to be
probably.
triple digits?
No, triple what you have right now.
I don't think we have a
Whoa.
big enough classroom, Mr. C.
It'll probably be kind of like 7th grade on like these sizes.
Yeah.
That'd be kind of fun.
No, 7th grade, I remember it. It's hard to remember.
would
It
be
felt
horrible. I
crowded,
would
but
not do that.
there really weren't that many people though.
100
felt crowded.
people?
When you take college
Oh,
on most universities, your first year or so taking classes, you go to these crazy huge
I don't have any other
classes
homework other than-
of like 300 people. You take your first English class, your first math class, your first science class, and it's like hundreds of people in one room.
Very simple, yes or no question.
And the good news, bad news about that is that, what's up?
and if you didn't finish, are you so you're in the gym.
Oh, I think.
Can I use a piece of graph paper?
Yep.
I've never seen mixed review exercises. Okay.
If we had not had a lot of snow days, I would start throwing those in there, but I kind of figured that
What?
You stood up, you're like, is he okay?
No, I said I have graph paper.
Okay.
How dumb do you think I am?
remember though, I also choose to do a day of review before every test, so.
You can be the one checking you.
Do it. Jack.
I have more paper than that, to be honest.
I don't know. I was curious.
Yeah.
Are you teaching or recording?
Yeah, I went over 10 minutes. I mean, I'm done now.
Yeah.
Okay. Because if I can ask you a couple questions.
Yeah.
If I didn't know if you were.
No. I say that as I literally am stopping the recording because I didn't stop it.
Not a recording.